Today, we'll be looking at Polkadot's unique hybrid consensus model that distinguishes it from traditional blockchain protocols. The approach is hybrid because it separates two critical functions of blockchain consensus: block production and block finality. It combines BABE, which stands for blind assignment for blockchain extension for block production, and GRANDPA, which stands for ghost base, recursive, ancestor deriving prefix agreement for deterministic block finalization. This dual consensus mechanism allows Polkadot to offer fast block production that ensures the low latency of the network, followed by secure finality that is not probabilistically based on depth, but one that is clear and deterministic. A block either is or isn't final. Let's break down how each of these components, BABE and GRANDPA, work together to form Polkadot's consensus model. BABE is Polkadot's block production algorithm that was inspired by the Ouroboros-Prowse consensus model used in Cardano. But before we dive deeper into it, what actually is a block production algorithm? Think of it as a game played by all the node operators, and the results are who gets to offer the next block. As an example, in Bitcoin, the nodes of miners compete to find a really low random number, and whoever gets it first creates the next block. In fact, Bitcoin is a bit agnostic to the real-world time flow. All it cares about is nodes finding those small random numbers. Sometimes it takes seconds to find, but other times it takes days. BABE operates a bit differently. It is a slot-based leader election protocol, which means it splits the time into small chunks called slots, and then tries assigning validators the task of block production in each of the time slots. However, unlike its predecessor, Aura, which operates on a round-robin basis, BABE introduces an element of randomness through verifiable random functions, or VRFs, to determine which validators are eligible to produce a block in each slot. Let's look at some of the core properties of BABE. Let's start with random leader selection. In each time slot, validators generate a single VRF output. Think of this as rolling the dice. If this output falls below a predetermined threshold, the validator is eligible to offer a block. This random process ensures that no one can predict which validator will produce the next block, preventing potential attacks such as DDoS or bribery attempts. This is a significant improvement over a simple round-robin mechanism, where the identity of the next block producer is always known in advance. And then there is fairness. One important thing to note is that there is only a single set of valid inputs to the VRF per validator per slot. So no multiple attempts are allowed. That is, each validator gets a single roll of the dice per slot. And lastly, there's potential gaps and forks. While BABE introduces many security benefits, it is not without challenges. The protocol has randomness in it, which allows for situations where no validator's VRF output meets the required threshold, resulting in an empty slot without a block being produced. Conversely, multiple validators can sometimes be eligible to produce blocks, leading to temporary forks. In such cases, Polkadot's fork choice rule, which you will learn about shortly, selects the chain with the most support, and the other forks are eventually discarded. While these events don't pose a threat to network stability, they illustrate the trade-offs involved in achieving secure randomness and decentralization. This problem of missed slots is now being addressed by a new block production algorithm being worked on called Sassafras, and its more lightweight cousin, Safrol, which are potential candidates to replace BABE. They are intended to launch together with the Jam upgrade in Polkadot 3.0,